Hello everybody, welcome back. We're going to look at examples 5 and 6. For 5, we have a different matrix A. It's still 2 by 2, well, because we can draw these grids with 2 by 2 matrices. This would be really hard with 3 by 3 matrices. And this A here is also diagonalizable, but this time with different column vectors. Now we have B1 is over here, and B2 is over here, and the entries of the diagonal matrix are different as well. And again, we're starting with x0 is 1b1. So here's 1b1 plus 2b2. That means x0 is right here. And that also means that the coordinates of this x0 relative to the columns of P are 1 and 2. Of course, the actual regular old-fashioned coordinates are like 5, 5, I think. But the B coordinates are 1, 2. Okay, now, again, we're going to use theorem 4.1 to plot x1 and x2. And the trick is still going to be that, well, first, before we do the trick, just the definition of xn means a to this power n times x0. But now, using the theorem, this is equal to d to the power n times the b coordinates of x0. Now, we know what d is. It's right here. It has columns 1, 0, and 0.5, like so. And the b coordinates of x0, we see why those are 1 and 2. Oh, I forgot the power n here. Whoops. And because this is a diagonal matrix, it's really simple to multiply this by the 1, 2 vector over here. We just get 1 to the power n times 1 and 0.5 to the power n times 2. So it's pretty easy to see what the b coordinates of x1 are from this. We're not changing the 1 here, that's the same, but we're doing 0.5 times the 2, like so. So those coordinates are 1, 1. So now when you do 1b1 plus 1b2, x1 is right here. Let's also get x2. Now the difference is the second coordinate, the b2 coordinate, is now smaller. The b1 coordinate is still unchanged. So we have still 1b1 plus now 1/2 b2. So that's where x2 is. And you can see what's going to happen is like the x3 is going to be even closer. You're just getting asymptotically closer to b1. You could probably say that b1 is the limit as n approaches infinity of this thing. But I didn't have room to write that there. So let's do the same thing with some other choices of x0. Like, what if you just start at a multiple of b1? So if that's your x0 there, the b coordinates of that are -1 and 0, because it's -1b1 plus 0b2. And you can see what's going to happen as you multiply this by powers of a. The same principle over here applies. It's just a different starting point. So this is still going to be 1 to the power n, 0.5 to the power n, multiplied by -1 and 0. And the 0 here doesn't matter. We're just getting -1 times 1. So actually, this one doesn't move. x0 is the same thing as x1, is the same thing as x2, is the same thing as xn. So that's what happens when you have an value of 1. Sorry, I shouldn't call it an eigenvalue because you don't know what that means yet. But when you have a diagonal entry in your diagonal matrix of 1, that means that multiplying this point times A repeatedly does not change it. And you can imagine if you have something else, like what if your x0 is over here? In this case, the b1 coordinate is 0. That's not going to change. The b2 coordinate is going to keep getting smaller, like so. Basically, everything's going to be getting closer asymptotically towards the b1 axis here. And if you're already on the b1 axis, like the orange one, then you don't move. So that's another kind of situation you can have by doing powers of a diagonalizable matrix. Let's look at one more. Here is example 6. Here we have the same b1 and b2 as the last example. The difference is that the diagonal matrix is different. It now has a 0 here, whereas we had a 0.5. And you can tell that makes the matrix itself comes out pretty different as well. Now we've got something totally different. Now we're still starting at the same beginning x0 point over here. So that means the b coordinates of x0 is the vector 1, 2. So there's that. And the same principle as before is going to apply, just with some differences. It's just that now we don't have 0.5 to the power n. That is now 0 to the power n. So this is just going to be 1 to the n times 1, and then 0 here. That's what's different. So x1 coordinates of b, making this change over here as well, is just going to be 0. So multiplying this x0 by a just slams you right against the b1 axis. And you don't go away from there after that either. So it doesn't nice and gradually approach the b1 axis like you did before. It just plops you right there. And you can see that you're going to get the same thing for any other power of a here. Another example, maybe let's say you start off here. If this is your x0, then a times x0 is going to be right here. That will be your x1. And that's the same thing that you're going to get for x2 and so on. And just like before, if you take a point that starts on the b1 axis, if that's your x0, then that's going to be the same as your x1 and your x2 and so on. All right, so let's look at part C. Which of these matrices from the last 3 examples are invertible? Let's start with this A here. Now there's a way you could see it's invertible using the diagonalization. We don't need to be that fancy. We can just see that the columns of A are not multiples of each other, right? You can't multiply this by any scalar and get 0.51 or vice versa. So they're not multiples of each other. You have a linearly independent list of 2 vectors here, and the invertible matrix theorem says that's got to be an invertible matrix. And if we look at example 5, this one also, if you look at these 2 columns, I can tell they're independent from each other. If you want to row reduce it, you could row reduce that to the identity. You could show that the columns of A span all of R2. You could actually go ahead and find the inverse if you wanted. There's a lot of ways to do it. What about example 6? Are these columns linearly independent, Or is it possible to write one as a multiple of the other? It is possible to write one as a multiple of the other. If you do negative 2 times the negative 0.2, negative 0.6 column, you'll get the 0.4, 1.2 column. So that means they're linearly dependent columns, and A is not invertible. Here's another way to see why A is not invertible. Because if you take this x0 right here, that is a solution to the homogeneous equation. Right? We just got x1. Remember, x1 really just means a times x0 here. And we got the origin. So a times this x0 here is equal to 0, which makes this have a non-trivial solution, which is another way of saying the columns are linearly dependent. And that also means A is not invertible. So, yeah. Sounds good. You got some more of these application kinds of problems to look at for the homework. Some of these are kind of tricky. We also have some sort of things to prove about diagonalizability. These are fun. I don't want to spoil it for you. Anyways, good luck with that, and I will see you later. Take care.